Okay. So here we go. So cryptography day 2 plan. We're going to finish the day 1 slides, and then I'm going to show you how to write and compile code on CoCalc. And that's not so much about CoCalc, it's just like how to write code on Linux. And then I'll introduce project 1, which will be due on September 17th, which is quite a while from now. So you got 16 days, hopefully, and I don't think it's hard. And then we'll go over the web work homework, and then if we have time, we'll do some slides on modular arithmetic. So that's basically what we're going to do. And I think I have to go actually open up some stuff. All right, so there's our classical crypto, but I should go to lecture 1. All right. So this is what we were talking about last time. Classical cryptography, we're sort of going through substitution ciphers and going over some of the basic terminology. And just like last time, this slide deck is, or if you want to call it that, this is really a Jupyter notebook. It's available to you on CoCalc if you want to look at it. All right, so substitution cipher, basically the idea is you have some collection of symbols, and then you substitute other symbols for those symbols. There are various ways to do it of increasing sophistication. First, we talked about the Caesar cipher, which is sort of the dumbest possible idea. And then the general shift cipher is the idea of shifting the alphabet by some number other than 3. And then we talked about the affine cipher, which is a little bit more complex. The affine cipher, you get a permutation on the alphabet that starts to look random. And here we also talked about inverses and stuff. This is going to be a big part of this class. So we'll often come back and discuss more inverse stuff. So this is the permutation that the affine cipher gives you. It looks more random than just a shift. And then we started talking about like actual, literally random permutations. And that's the general substitution cipher, where you take a permutation that really is random. And I also pointed out this thing, which is going to be also an important part of the course, which is a major mistake in cryptography that happens often, almost always when something happens disastrously from a cryptographic point of view. It's because somebody thinks they're using a number that's random that's really not random. So here where I seed the NumPy random number generator with 0, this random permutation is only as random as the seed. And so you can just go through the headlines, on Slashdot or some other tech website where you look at cryptography disaster after cryptography disaster. And frequently the thing that goes wrong is that somebody picks a random seed that's actually not truly random. And the reason that that's so often what goes wrong is because the algorithms themselves, like AES and DES or whatever, stream cipher, those algorithms are really well tested, and there's basically nothing wrong with them. Like, you can't crack a strong cipher. Snowden released some stuff in 2013, and even that NSA can't crack, AES 128 or whatever. And so the way that that people make disastrous mistakes is that they use those algorithms wrongly, and those algorithms often call for some truly random information, and then the person who's writing the code uses a random number generator that's just not adequate. And we talked about bits of security. I'm going to come back to this when we talk about the web work homework in a minute. Okay, security, the general substitution cipher. We said that the general substitution cipher actually does have enough bits of security. It has 88 bits of security, which is strong enough for a real cipher, but it has a big problem, which is it doesn't disguise the statistical profile of the plain text. We talked about how the statistics of the letter distribution in a work of written English doesn't really depend on the book. The Shago, the Mighty Buffalo, and A Girl in the Plains Country, or Of the Plains Country, the letter frequency is basically the same for those two books, or really any book written in English. So one way to crack a general substitution cipher is to look at the letter frequency that occurs in the ciphertext and then use the profile of the letter distribution in written English to sort of reverse engineer what the associations must be. So this F is E because E is the most frequent letter in English. And then these letters that occur with like practically zero frequency, like G, M, T, and V, those are going to be the weird English letters like J, Q, X, and Z. And so by making these connections, it's not always a smooth process, but just by fiddling around, you can crack any substitution cipher. If you don't get a lot of ciphertext, then the statistics are disguised by the fact that you just don't have a big sample. So like here, this is kind of a small ciphertext down at the bottom. And I'm sorry, I'm trying to make it bigger and it's making the screen a little bit weird. So you can try to crack this if you want to, but it's kind of short. So when you don't have too much ciphertext to work with, one trick you can do is instead of looking at the single letter frequency, you can look at bigrams and trigrams. So bigrams are pairs of letters that occur in sequence. So actually, the substitution cipher is even kind of worse than we said. So the single letter frequency distribution is the same, but there's another thing that leaks information about the plain text, which is that the substitutions show up in the same order as the letters in the plain text. So you can exploit that by looking at bigrams, for instance. Bigrams are just pairs of letters that occur in sequence. So QU has a certain probability of occurring in some written English work. So this is non-zero. And certain other bigrams have basically no probability of occurring, like ZW. Like when in written English do you ever see W followed by Z? The only way it could really happen is because we're taking spaces and punctuation out of the plain text. So it might happen that, some word ends in Z and then the next word begins in W. And so that's basically the only time you're gonna have that happen. And you can Google like bigram letter frequency table, and oh, here's an online calculator. I was actually just looking for a chart, so maybe I'll search images here. I'm sorry, I'm just kind of, oh, yeah, did you have something to say? I'm using DuckDuckGo, which is not super sharp maybe. So here's they're calling the single letter frequency, they call those monograms. If you go down to bigrams, so these are, I'm gonna make this bigger. These are the most common bigrams in the English and written English, I-N-O-U-Y-O, is that right? Seems to be anyway. And then you can do the same thing for trigrams, like Y-O-U. You would think T-H-E would also be a common trigram. Oh, I see. This just pertains to what's written in this text. So this is like a bigram cracker. This is why I can't give you guys an assignment like solve this puzzle or whatever, because you could just use these online tools, which I guess is okay. It just makes things different. Like, but anyway. So if you type something in this box, what you'll see here is the frequency counts for the bigrams that occur in order of decreasing frequency. When you get a short amount of ciphertext, actually maybe we should go back here and I'll copy this challenge that I gave you guys. Where is it? Right here. This is going to make the screen explode. Copy this. Okay. Come back here, paste this in. All right. So now this says that RL in this in my ciphertext here, RL is a commonly occurring bigram. So what you could do is you could compare that to what is the most commonly occurring bigram in English. Unfortunately, I haven't memorized the answer to that question, but RL probably corresponds to that most common bigram, whatever that is. And you can do the same thing with trigrams. So the most common trigram in the ciphertext here is SBQ. So like a natural guess is maybe that's THE or whatever the most common bigram is in written English. Okay. Whoa, and so it looks like, somebody have a question? Like, you can always raise your hand. There's some button for raising your hand, or you can just talk. You can put on loud music and then unmute yourself, open your window.
Professor?
Yes.
Yeah, quick question. Are these your office hours or?
Oh, no. This is just class time. I'll be here to answer questions at 1:30. And I think that's going to be a regular thing. We'll see how crowded that is.
Okay.
Or if that time doesn't work for you, we can try other times.
Yeah, so I'm still not clear at what time classes are. Would you be able to tell me?
What time our class meetings are?
Yeah.
Our class meetings are always at 10:50 on Tuesdays and Thursdays.
Tuesday and Thursday. Okay. Just because I'm like on the West Coast, so it's a bit.
Yeah. So we're just trying to stick to the usual meeting times. In retrospect, I really wish that I had made these asynchronous because I have a small child and my wife basically has to take the day off on Tuesdays and Thursdays, which is kind of weird.
Mm-hmm. Okay, thank you.
But I'll try to always be here at, well, I will always be here unless I notify you like a long time in advance.
Mm-hmm. Okay.
All right. So there's bigrams and trigrams. So there's all the things that we've been talking about so far are what's called monoalphabetic substitution ciphers. That means that like there's one symbol is always has a substitution which is the same, right? So in some substitution maybe F is substituted for E, and every time E shows up, F is always the letter that's substituted. That's called a monoalphabetic substitution cipher. You can do something a little bit more complicated, which is, the cipher can have some kind of internal state that updates. And maybe when the cipher is in a certain mood, E gets substituted, F gets substituted for E, but then the state of the cipher changes. And then the next time E is encountered, when the cipher is in this new state, some other letter is substituted for E. It's called a polyalphabetic substitution cipher. And the most famous polyalphabetic substitution cipher is the Enigma code from World War II. Some of you guys have probably seen this before, right? This is like, kind of looms large in everybody's imagination. They would, people died to recover these machines from submarines and stuff like that. And if you've seen the movie, The Imitation Game, the movie about Alan Turing, it was all about cracking the Enigma. That movie is not so factually accurate, but there was, there was Bletchley Park in the UK that broke the Enigma code without Germans being aware that the code was broken, and some people say it saved like a year or two off the war, 13 million lives or whatever. So the British cryptographers did amazing work in World War II. But the Enigma machine is basically a polyalphabetic substitution cipher. You can see here there are keys, and interestingly, it's not quite QWERTY, right? Some letters are missing, like there's no Y. That's interesting. The Y is down here. Is that European keyboard layout? I have no idea why that's the case. So you would push one of these buttons, and then the light corresponding to the substituted character would light up. So maybe you press Q, and then this light comes on, which means B is what's substituted for Q. So the thing that made this polyalphabetic substitution cipher is these rotors here. So every time you would press a key, this little rotor would spin. And then once this little rotor spins all the way around, this big rotor spins. And once this big rotor spins all the way around, this bigger rotor spins. So some different iterations had different numbers of rotors, and the initial setting of the rotors is the key, actually. So that's what the Germans had to change in a synchronized way, the initial state of the rotors. And then somebody could, you know, set the decrypting Enigma device, set the rotors and the corresponding decrypt configuration, and then type in the ciphertext, and the plain text would come out. So sometimes when you would type Q, B would come out, but then when the rotors changed to a different position, when you type Q, something completely different would come out. So polyalphabetic substitution ciphers, as you can infer from the fact that the Enigma was cracked, are not secure. It's not totally trivial to break this thing. You know, the first electronic computers, the Colossus machines at Bletchley Park were built to crack this. There are some Polish cryptographers that did much more work on cracking the Enigma than they ever publicly get credit for. But the English were in some ways just sort of imitating what the Polish were doing. So here's something that is a lot more simple than the Enigma machine. That's also a polyalphabetic substitution cipher. It's called the Vigenère cipher. There is some kind of like diacritical mark or something that goes on Vigenère over the E, and I haven't written it there. I'm sorry, I was in kind of a hurry. So the idea with the Vigenère cipher is you have plain text, whatever plain text you want, and then there is a key stream. So there's just some keyword, which in this case is lemon. And in the key stream, the key is repeated over and over again, however long the plain text is. So if the plain texts were longer, this would keep going lemon, 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 lemon. And the way encryption works is, so just like in the substitution ciphers, the Roman letters are converted into numbers. So A is 0. And then L is whatever number in the alphabet L is. We could figure that out really quick if we wanted to. So what is the number for L minus the number for A is 11, okay? So L is 11. So then you add these two numbers, 0 plus 11 is 11. So that just means that there's an L there because 11 is L. If they add to a number that's greater than 26, then you spin around and reduce modulo 26. So where could that happen? That might happen here with like a K plus or T plus M probably happens, right? So what number is T? So the number for T is 19. And then if we add in the number for M, it's the number for M. So this will be word M minus word A. Okay. So this is the sum of those two. So it adds to 31, which is more than 26, obviously. So you have to reduce this mod 26, and you get 5. And so the cipher here is the 5th letter of the alphabet, which happens to be F. Okay. So this is obviously more complicated than a simple substitution cipher. If you try that letter frequency attack that we discussed earlier, what you'll see is that it appears that all letters are equally likely now. So instead of this spiky distribution like this, where every letter has like a unique frequency, it'll instead just look like a block where every letter is approximately equally likely to occur. So that makes it much harder to crack. So you can't just do the letter frequency attack. So if you really want to know how to crack the Vigenère cipher, there's a Wikipedia article on something called the Kasiski examination that explains it all. I'm not going to go through it in detail, but the way it basically works is you guess the key length. So here, you can guess it just by trying lots of different possible key lengths. So here you see that this A here, and this K here are both on the same letter of the key. So if you look at every, and the key here is 1, 2, 3, 4, 5 letters long. So now if you look at every 5th letter of the ciphertext, like this L and this V here, and then later this H here. So if you were to make a frequency table for those letters, What would happen is, because all of those letters are being shifted over by L, that's how all of those ciphertexts are being produced, then it's just like a shift cipher. If you look at every fifth letter, what you would see is a shift cipher. And you can recognize that by looking at the frequency distribution table that pops out. So when you guess the length of the key incorrectly, you'll see a flat block here, like a flat top haircut. But when you guess the key length correctly, suddenly this pattern pops out. So you know that you guessed the key length correctly, and then you can figure out what the letter of the key is corresponding to this by doing the letter frequency attack. And it's kind of tedious, but basically using that trick, you can break the Vigenère cipher. For years, this was called Le Cipher Indefeatable or something. I'm sorry, my French is bad. But it was called the Unbreakable cipher. And the Confederates famously used this cipher in the American Civil War. They didn't change the key very often. I think the key was like General Lee is awesome or something like that. And all of these old ciphers were eventually cracked. All right, so this is a good opportunity to introduce something called the chosen plaintext attack, which we haven't talked about yet. But let's just review. So last time we talked about a couple of things. I'm going to write on the screen here for a second. Let's go up to the top. Come on down. All right, so what have we talked about so far? We have the ciphertext only attack. So this is the most difficult attack to implement if you are the cryptanalyst. That's the person who's trying to break the cipher. When you have the ciphertext only, then all you get to see is the ciphertext. So you have the hardest job. And it's a little bit better if you are in a known plaintext attack situation. So this is a different situation in which you have the ciphertext, but you also know what the corresponding plaintext is for some of the ciphertext. So that helps a lot, okay? And now what we're talking about now is an even better situation for the attacker, where here with a known plaintext attack, you didn't get to pick the plaintext. It was like probably you assumed that the letter started with hello or something and you got lucky. So the plaintext that you get to see is hello. You don't get to choose it. It's just that's what the known plaintext happens to be in that situation. But in a chosen plaintext attack, you're assuming that the attacker can actually choose some plaintext and then see what the encryption would be. This is called chosen plaintext attack. Okay, and all modern ciphers have to be secure, at least under chosen plaintext attack. So let's look at a chosen plaintext attack on the Vigenère cipher. I'm gonna stop this. Okay, and so I should have asked you guys. So if you were going to choose some plaintext to reveal the most information about the Vigenère cipher, what plaintext would you choose?
The alphabet, maybe?
Yeah, the alphabet is a good idea. That would be my second choice, I guess. But look what happens if you choose the plaintext to be all A's. This is like Charlie Brown when Lucy moves the football. So the thing about this plaintext is, just by the way the cipher works, A is 0, right? So if you encrypt all A's, what the ciphertext just is the key repeated over and over again. So if you can choose the plaintext that gets encrypted, you can trick the system into immediately telling you what the key is. So the Vigenère cipher is very vulnerable to a chosen plaintext attack. You just choose all A's, and then the ciphertext is just the key. So you're done. So you have to be careful about that. You might ask, like, what idiot would encrypt all A's for you? And this is like a common question in a cryptography class is, what idiot would blank, blank, blank? And the idiot that would do that is a computer server that doesn't, that just follows really strict rules. And it it doesn't have a brain that, you know, understands context in the same way that you and I do. So the server will do really simple things, stupid things like encrypt all A's and things like that. And there are situations where you can do chosen plain text attack. This is actually a realistic assumption in a lot of situations. Like maybe you and I use the same bank. Like I use Wells Fargo, and they use a certain cipher. So maybe I can like make a money transfer or something, and then I'm eavesdropping, and I can see the encrypted version of whatever money transfer I made. So by doing different money transfers, I can see different ciphertexts. And then if they use the same key for you as they do for me, then and if a chosen plaintext attack will work in this situation, then I can decrypt your money transfers because I can do the chosen plaintext attack. Yeah. All right. So okay. There's another kind of attack model. These are called attack models that maybe we'll talk about later. It's called chosen ciphertext, which is kind of strange. And in that assumption, you get to choose any ciphertext you want, and then you get to see the decrypt. So then you can say, what idiot would decrypt a message for you if this is supposed to be a secret cipher? Maybe some server would, but if you have a cipher that is resistant even to chosen ciphertext attack, then maybe that's just, it's good to assume that the enemy is more powerful than they are, then you don't have to worry about weird things happening. So all of these have been broken. There are no secure pure substitution ciphers. So there's no theorem or anything that says this as far as I know, but it's true. So no cipher, whether it's monoalphabetic or polyalphabetic, that relies purely on substitution is secure. So what people found later toward the second half of the 20th century is even though no substitution cipher is secure, substitutions are an important part of ciphers that are secure. If you mix substitutions with permutations over and over again, then you get very strong ciphers. And those are the kinds of ciphers that we still use today, like DES and AES, which you might have heard of. The way that those work is they do substitutions, and then once they do a substitution, then they permute the result. And so they change not only the characters, but then they rearrange the order in which the characters appear. And then they do another substitution, and then they shuffle the order in which the characters appear. And then they do another substitution. There's some number of rounds of this, usually like 16 rounds, for example. So after that, nobody knows what in the hell is going on. So nobody's found a way to break. These things are called substitution permutation networks. And after 17 or 16 iterations of this process of substitutions followed by permutations, right now, nobody knows how to undo that. All right, so let me, I think I'm sharing my whole desktop here, so maybe we can come back to the plan. All right, so we just finished the day one slides. So now I'm going to talk about writing and compiling code on CoCalc. So that, you know, you can live your life without knowing how to do this. But you know, about half the coding jobs out there are actually on Linux systems or Unix, I guess. So it's good. Actually, it's my first coding job was on a Unix system, and I had not had a lot of Unix training, and it was a sharp learning curve. So let's just let's talk about that. Let's go to CoCalc here. I'm not going to click on this and share everybody's personal information, but I see that a lot of people have not either created their account or they haven't paid the $14 yet, and there are 3 days left. I really encourage you to do that, because after those 3 days are gone, the deal, the $14 for the whole semester deal goes away. And this has happened to me before in previous semesters. There's like, professor, I didn't pay the money, and now they say they want $14 a month instead of $14 a semester, so I have to pay $45 instead of $14. And this is like so annoying, because it is, you know, it's probably the student that had a hard time coming up with $14 that now has to pay $45. And I've just given students the money before, but I don't do, you know, that was when I could like give students 20s, but I can't do that anymore. So please just sign up and pay your $14 if you can. You know, if you're playing your cards right, that's the only $14 you have to pay for this whole class. So now I think I do need to look at this, and I'm gonna have to trim this out. Yeah, I'm gonna have to trim this out of the video later, or make the video private. But I have to show you this. So this is.
I cannot do shit with it anymore.
What? I'm sorry. Could you say that again? So I have to. I didn't know how to get here without going there. So you have an assignment assigned here, which is project 1, and you have 2 handouts. One of them is day 2 slides, and the other is the lecture notes that we just went over. So let's open up a let's open up. I'm gonna if nobody has a question here, I'm gonna mute that because that's kind of noisy. And all right, I don't know. So let's make a directory just example. You can do this wherever you want. So I'm going to, you know, maybe you want to create a new C++ program or something. So I'll create a file, hello.cpp. Right, I'll just create hello.cpp. So now this is an IDE. I'm going to click over here on split window, and then I'm going to change the split window to a terminal. Okay, and let me try to make this a little bit bigger. Sorry, I'm trying and failing to increase the font size. Anyway, let's just do hello world here. Include standard IO. Is that right? Do this. Okay. Right. And so now I'm in the same directory over here. So I'm going to compile this program using the GCC compiler. So I actually, yeah, right. So I'll just type the name of the file, hello.cpp, and that compiled. And let's look in the directory here. So you can see now in this directory there is hello.cpp, and there is also an executable. So we can use a hex editor to see what's in the executable. But you guys have done this in some other class, right? This is just the machine code corresponding to the compiled program. Now, if you want to run that compiled program, I'm doing a dot followed by a slash, and now I'll type a.out, and it prints hello because this is the hello world program. So that, in a nutshell, is how you can work here if you want to. One nice thing about working here is that we can do live collaboration where you work on your code and I work on your code, and we can see each other's cursor, and we can also be talking over Zoom at the same time. So I find this is like a very effective way to do office hours. And it kind of makes your work portable also. You can use a computer wherever. This is just not something that you wouldn't necessarily care about, but if you want to give the output a name besides a.out, you can call it hello if you want to. So that produces an executable called hello, which you can then run like that. Okay. So I'm going to come back here, and now let's look at your first project. So I've assigned it to everyone, and I'm going to go through my version. Your version should be very similar. I'll go into projects, project 1. So you now have this, oh, it even says the due date. That's convenient. So the place to start here is to open the description. So here you have the description in PDF form. There's also the description in Markdown. So you can open up whichever one you prefer. And so this takes a long time to go through. But what you're basically doing here is you're going to write some code that implements a substitution cipher, and then you also have to crack a substitution cipher. So this first part of the code here just explains how a substitution cipher works. This explains the files that are in the directory. Let's just look at those together right now. Some of these are binaries, like these things here without file extensions. Decrypt, for example, is a binary. That means that it's compiled code. And this platform, CoCalc, does something really unfortunate. If I were to click on this and open it, then that would corrupt the binary. Because if I open it in a text editor, CoCalc would add new line characters to the end, and then it automatically saves changes. Drives me crazy. So if you open a binary on CoCalc, it gets destroyed. Inevitably, despite me saying that, this happens every semester, people will click on those binaries and open them. So for that reason, I also gave you this folder, binary backup. If you look in here, you can see that the code that the programs that you basically need to write are the encrypt program, the decrypt program, and the histogram program. So if I open a terminal in here, I'm going to do new terminal, right? Everybody see how I did that? New terminal. So now I'm working in a terminal and I can interact with some of these programs. So let's see what they do. So let me run maybe we should run clean first. Actually, clean is already written for you. So all this does is this takes out punctuation and it converts everything to capital letters. And the program is already written for you. When you're dealing with it in this interactive way, the way I stop is to press Control D. Control D is EOF, end of file, in Linux. And from the command line, there are other ways to interact with clean here. Let me just create another file here. So I'll say some things like, my name is John Jacob Smith, and put this in a file. Okay, so I can also run this file, run this program on this file by doing redirection. This is input redirection. So what I did is I just kind of poured that file into the program. Another way that I can interact with this program is by piping data in. So this cat command dumps code, dumps text to the screen. I can pipe like this. So what this does is it says the output of the thing on the left of the pipe becomes the input to the thing on the right. So when I do that, it also just gives the input to the clean function. All right. So when I've done this and I want to maybe save the result, I'll just call this clean text.txt or something. So now the contents of that file are like that. And so now I want to encrypt that. So let's see how this would work. So I'll encrypt, and I want to give it clean text as input. And so what comes out is the result of applying a substitution cipher to the input with key K. Let's do it let's do it our own chosen ciphertext attack on this. So I'll just type A. What comes out? K. All right. So what this is doing is it's doing a shift cipher with key K. So that's what you have to implement. And I've already written a lot of the code for you. Let's look at encrypt.cpp. Right. So this is what you have. Your code is actually only missing one line. And you'll notice that this is using C style IO. To be honest with you, I'm much more comfortable in C than C++. But you can still do C++ here, but you don't have to. I mean, all you have to do is do the actual substitution thing. So here, what are you doing here? You're getting some input from standard in, and so what is standard in? That's just, we just experimented with standard in. Standard in comes from either typing on the keyboard, or from piping information in, or from input redirection. And it's really convenient because you can, if you prefer to type from the keyboard, you can do that. If you have a file that you want to use as input, you can just redirect it in. It's extremely convenient. So what this while loop does is it goes through and it gets each character from the input until it encounters the end of file code. And what you have to do here is you have to do the substitution. So you have to replace the character C with, it's kind of deceptively complicated actually, because C will be an ASCII character. So that means, and it'll be an uppercase letter. So it'll be something in the range 65 to 65 plus 26. Now you have to turn that into a number between 0 and 26 corresponding to the letter. I've already shown you how to do that. You do that by subtracting 65, which is the ASCII code for capital A. Once you convert it into a number, then you have to add the key, but the key also needs to be a number. Right now it's a character, but you need to translate that character into a number in the range 0 to 26. When you do that, you add them mod 26, that gives you another number. Now that is not an ASCII character, it is a number. So now you need to do the opposite and take that number and push it up by 65, just add 65 to it, and that makes it be the corresponding letter, and then that's what the output is supposed to be. So it's easy, but it's also challenging. All right, and the other thing you have to do is the opposite of that. So you have to do the decryption. So this is just checking that the user does the. Here you have to specify the key on the command line. I'll show you that in a second. But the only line that you need to add here is like the corresponding decrypt line here. So you know, instead of adding the key, now you're going to subtract the key. There's one thing that is a little bit tricky with C and C++. Can actually do an experiment here. Let's come back here. So what if I say that int I is equal to -12 mod 26. This could happen when you're doing decryption, because in decryption, you know, what you're supposed to do is like, you know, y is equal to x minus k mod 26. So this is how you do the decryption for the shift cipher. So if k is bigger than x, then you're going to get a negative number. So what happens when you have a negative number and you try to reduce it mod 26 in C or C++? Let's see. So you print. Let's print this. I haven't done this in a while. I hope I'm doing it correctly. All right. So I'll save this. Now let's compile it and run it. Okay. All right, so what you'll see is C or C++ thinks that -12 mod 26 is -12. So that's gonna mess everything up. And in some sense, that's kind of the wrong answer. Like if you do the same thing in Python or another language, if you ask, what is -12 mod 26, you'll get the right answer, which is a positive number. We want our answers to be in the range from 0 to 25 inclusive. All right, here's a way you can always make this work. So instead of just doing, so here's what we're doing in the abstract here is x minus k. If you add 26 in here, that 26 will disappear mod 26. But what it will do is it will force the output to be a positive number instead of a negative number. So I'm going to make that change to the code there. I'll save that. Let me quit Python, recompile, re-execute. And what I consider the correct answer here, 14, comes out. So the positive solution comes out. It's just an annoying detail that you're going to have to deal with. All right, so let me quit this. And let me go back into the binary backups directory and show you that stuff that I alluded to about the decrypt. But first, let's encrypt something. Encrypt. Let's encrypt clean text, so it comes out to be that, and let's call this the ciphertext .text. Okay. So now we have a ciphertext file containing that stuff, and we want to decrypt it. So if I just do decrypt and press enter, oh, sorry, this one, shoot, this is the one that's been corrupted. But let me fix this right now. Oh crap. I need to fix this. So I'm gonna tell you about this on Thursday, and hopefully nobody's gonna get that far before Thursday. So what happened here is I myself was stupid enough to click on this binary and open it, and it got corrupted on CoCalc. So this is no problem, because actually maybe I can do this right now. If I go into project 1 solution, then I also have decrypt here. Does this one actually work? Yeah, this one actually works. So I'm going to copy this one into project 1. Sorry, decrypt. And then, whoops. Right? And also do the same thing for the backups. And I'm just going to replace what I have already given you with this. So that will head off a lot of trouble. All right. Anyway, okay. So here we are. We're back to where we were before. We're just showing you how the decrypt function works. So what it'll say is that you need to tell it a key character. So you need to tell it what is the key. So in the case of encryption, it was baked in that the key was K, but now I have to tell it what the key is. So let me tell it that the key is K. And now if I type some stuff like blah blah blah, it gets decrypted. But the reason that nonsense comes out here is because I'm typing in plain text, but what it's doing is decryption. So all right. So let me quit this. Now let's do the whole thing. So let's pipe in the ciphertext, and what you get now is the correct decryption of the plain text, which is my name is John Jacob Smith. So there's one other program that you have to write, which is the histogram program. You have to write this one completely from scratch. So let's do the histogram program. Let's pipe in, what do I call this? This file, the thing that has the plain text in it. Yeah, but it's clean, right? We want the clean version. Whoops. All right. So there's the clean version. So now let's see what happens when we run the histogram program on that. So I'll run the histogram program, and I'm redirecting in the clean text, and it gives me a histogram showing the letter frequency there. You know, when I wrote my program, I put the letter first, but I kind of regret it. I wish I'd actually put the number first, because if I had done that, then using the command line, I could easily have sorted these in order of frequency. When you do it, despite what the instructions say, I'd really suggest you put the number first, because then you can just pass this to sort, and it gives you the letters in nice order. So the point of having the histogram is that you can run the histogram on the ciphertext and the clean text and see what the correspondence is. So like A here in the plain text occurs with, it's 9.1% of all the characters. So I look down here at the ciphertext, and C is 9.1% of all the characters, but so is K. Actually, K is the correct answer here. And you can see what the correspondence is. So it doesn't make a picture, it's just command line output. But that's basically what project 1 is. To do the encryption and to do the decryption, you just need to add one line of code, which is a tricky line of code. Everybody always succeeds at this. This is just an exercise. And then to write the histogram, you have to write it all from scratch. In previous semesters, students often fail at being able to write the histogram. If you can't write it, you're not going to fail the course. On the other hand, you should be able to write a histogram program depending on where you are in your undergraduate major. And so that is everything about Project One. Anybody have any questions on what I just said?
Yeah, where exactly are we writing our code?
You can, if you want to, you can download this entire folder. Like I'll come up here, you'll have something that looks like this. If you want to work completely on your own computer, you can check this box and then click download, and then write your C++ files on your own computer. And then once you're done, you can upload that back into your, upload your C++ files back here, and it'll be collected automatically from this directory on your CoCalc project. If you prefer, though, you can work right here also, and I kind of like that because I can sort of help you. But if you prefer working on your own machine, lots of students prefer working on their own machine. You can do that too.
Okay, thank you.
Okay, any other questions? All right. Well, any other questions? All right, so I'm going to come back here to the plan and see where we are. So we talked about Project One. Now let's look at your homework, and I can help you with a couple of these questions. So I'm going to come back to the browser. I'm going to use Firefox here.
Professor, someone typed in the chat a question.
Oh, sorry. Okay, let me stop the share. Go to the chat. So professor, for coding, are we going to stick to Python or C++? For this project, you kind of have to use C++ because it's already set up. There are a couple of reasons you have to use C or C++ for Project One. With Python, Python has a library called SymPy that will basically just solve this problem. And so we don't want people to use that library. Also, if you feel like you have a really original solution to this in Python, then I can give you credit for it, but it's so damn easy to do it in Python is sort of the problem. So you're doing something almost completely different from what everyone else is doing. But I've let people do it in Java in the past. Really, the easiest way to do it is going to be to just add that one line of C or C++ code. But if you really, really want to work in Python here, we can talk about that. But you can't just use the SymPy library. How do we turn the project in? The project will be automatically collected from your CoCalc folder. So you just have to make sure that your C++ files are in your CoCalc folder by September 17th. And when is the project due? The project is due September 17th. Okay. All right. So I'll go back to my desktop. Okay. And right, so we were going to go to web work. So here's web work. This is my calculus course. Let's come back to crypto. Okay. All right, so let's look at the chapter 1 problems. So I'm not gonna say a lot about these first few. Decrypt the following messages encrypted using the Caesar cipher. You could do project 1 first and then use your solution to do this, or you could just do it by hand. Or you could just, if you know, I don't care how you get the answer to this. If you want to write a quick Python program, if you know Python, you can use the SymPy library. But if you really don't understand how it works, I suggest doing at least a couple letters by hand. You know, doing things by hand really helps you understand what's going on. You have the cipher, which it's the Caesar cipher. So what you have to do is, instead of adding 3 to all of these, you have to take 3 away. So -3 is the same thing as adding 23 mod 26. You can do it either way. And then type the result in here. We have a couple problems like that. Okay, so encrypt the message halt using these shift ciphers. So these are all shift ciphers with different keys. And so you're going to type in the ciphertext for halt 3 different ways. Okay, if you have done project 1, then you can use your encrypt function. You know what? Oh, I just realized you can use the binaries that I've already given you, actually. Oh, forget I said that. And okay, for number 3, encrypt the message math by applying the, so this is a, what cipher is this? We've seen it before.
Affine.
Yeah, this is the affine cipher. So this is asking you to encrypt encrypt the message math using the affine cipher with different affine cipher keys. Okay, and now this is probably the most challenging problem that we've seen so far. So you're given this ciphertext and you know that it was encrypted with this key, and you have to do the decryption. So that's in the notes that we have talked about. If people have big questions about this, I'll be here at 1:30, and you're also always welcome to bring this up in class. If you know, at the beginning of class, when I say, anybody have any questions, you could say, can we do homework problem number 4? And I'll say yes, and we'll come here and work on it a little bit.
How many attempts do we have at every problem? Because I see it shows preview answers on the bottom there.
Yeah, it's infinitely many.
And would it tell us the right answer afterwards?
If you get the right answer, it tells you that you're right. Yeah. Okay. All right. So this is the main reason I'm here, because I wanted to go over this with you because it's a little bit challenging. This question is randomized, so everybody will get different numbers. So let's just do this together. I'm going to split my screen here, and let's see if I can find I don't have my whiteboard program open, but I'll open it here. And let me minimize this. Okay, I want to zoom in a bit and see if my whiteboard program is working. Yes, it is. Okay, so let's just go through here. So suppose a password consists of 12 ASCII characters. Your number will be different. You can review the ASCII characters here. Exactly 128 of these codes are for printable characters. And let me just show you what that means in case you forgot. So if you look at the ASCII characters, a lot of them don't print. So in decimal, it goes from 0 to, this is interesting. So this actually, the assumptions here are a little bit wrong, because these early ones, like if you try to print these to the screen, nothing happens. We'll just assume that there are 128 ASCII characters. This is actually a little bit of a lie. Like about 108 of them are actually printable. So, but anyway, just assume that this is true. So we'll assume every character in the password is printable. What is the size of the key space that consists of passwords of this form? So this is a Math 204 question. So you have 128 symbols that you can write down, which are the ASCII symbols, and you're going to write down 12 of them. 4, 5, 6, 7, 8, 9, 10, 11, 12. So how many possibilities are there for the first thing that I write down?
128.
Yeah, 128. And how many possibilities for the second thing that I write down?
128.
Yeah, 128. Okay, so you can see where this is going. So what is the answer to this first question?
128 to the 12th power.
Yeah, exactly. 128 to the 12th power. Okay, great. All right. So now it says, what is the equivalent key size and key length in bits? So this is is in the lecture notes, but let me just remind you. So to answer that question, we have to find out 2 to the n, where n is some unknown amount, is equal to 128 to the 12th power. So there are a couple ways you can figure this out. You could do n equals log base 2 of both sides. Another way you can answer this question is you can see this as 2 to the 7th to the 12th power. And then what is 7 times 12? 70 to 90, 94? I don't know.
84.
What is it? Don't trust my arithmetic.
84.
84. Okay, thanks. Okay. All right, so the answer is 84, right? So this n and this 84 correspond. So the answer here is n equals 84. And now, so all of that you probably could have done on your own. I was worried about these later questions. Come on, scroll down thing. All right. So now this is a really important question to be able to answer if you're evaluating cryptographic security. So assuming that you could check one password every 10 to the negative 6 seconds. So it's going to be helpful to translate that into the number of passwords per second that you can check. So how many passwords can you check per second here under this assumption? You could check one password every 1/1,000,000th of a second, 1 microsecond. You check one password every microsecond. How many passwords can you check in a second?
10 to the 6th.
Yeah, exactly. So you can check 10 to the 6th passwords per second. All right, so now it says, what is the worst case running time for cracking this password by brute force search in days? So the way you do this is put the number of possible passwords, which you already know. That was the answer to the first question here, over the number of passwords per second. And if you just look at the units here, you can see that the answer is going to be seconds. Right. And then once you get the answer in seconds, you have to convert that into days. So how do you do that? You take the number of seconds, divide it by 60. What is that? If you divide the number of seconds by 60, what does that give you?
Minutes.
Minutes. And then if you divide that by 60, what do you get?
Hours.
Hours. And then if you divide that by 24, you get?
Days.
Days. And so we're done. Okay. All right. And you type that number in there. Okay. So now we're going to, in the second, or I guess whatever, it's not quite the second, but now assume that the user used only 35 characters from the keyboard. Then you have to redo all this stuff under the different assumptions. And so these, I don't think I'm going to do these because it's exactly what I just showed you how to do. And then it says, supposing you used only 35 characters, how long is the shortest password that achieves 80 bits of security? This will hopefully be a surprisingly big number. Okay, and so there are a couple more questions which maybe we should go over. Next problem. Which numbers in Z42 are relatively prime to 42? Let me just remind you what this means. So Z42 is just the numbers 0, 1, 2, blah, 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 up to 41. And the answer to this question is numbers in Z42 such that the GCD of A and 42 is equal to 1. If you want to, you can sort of simplify your life here by using a terminal. I'm going to type Python 3. You can do this on CodeCalc if you want to. I'm going to import numpy as np. And from numpy import GCD. That worked, right? Now I can do GCD. Blah, 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 blah. Okay. So those two numbers are relatively prime. If you pick two numbers at random, there's a pretty good chance they're relatively prime. Okay, so I'm just saying this because maybe the easiest way to do this is to write a short computer program. If you want to do it in C or C++, then you're welcome to steal code from the internet on how to compute GCD. You would just loop through all 42 possibilities, and just check that the GCD is equal to 1. See how many satisfy that. Next problem. Which numbers in Z20 are relatively prime to 20? This is literally the same question again. Next problem. Okay, so this is about modular inverses, and this is randomized, so maybe we can solve the first one together here. The answer is not 0.25. We're looking for the inverse of 4 mod 11. If you look at the notes that I gave you that we've been following, it talks about this notation. So what this is notation for is so let me remind you. So 1 over A mod n is supposed to be some number b such that a times b is congruent to 1 mod n. So that's what the reciprocal means in this case. It doesn't mean literally divide. Let's try to answer this question. So what number, maybe I can make some space over here. So I have 4, and now 4 times something is congruent to 1 mod 11. So can somebody just figure out this number just by thinking?
8.
Let's see, 8. 8 would be -1 because 8 times 4 is
Yeah,
30.
you're right. Sorry.
Huh? There's only 11 possibilities. 4 times 2 is congruent to 8, which is just 8 mod 11. What about 4 times 3? This is 12. What is 12 mod 11?
1.
1. That's the answer.
Yeah.
Okay, so 3 would be the answer there. Okay, and you do the other ones same way. Next problem. Okay, so now this is asking you to do modular exponentiation. What we'll see later is, you can reduce. Let me just show you this. Let's clear some space here. So let's look at this one, 7 to the 6th power. So we want to do 7 times 7 times 7 times 7 times 7 times 7, and then reduce the answer mod 10, which is no problem. Calculators can handle that. But there's actually kind of a smarter way to do it than just brute force. This has nothing to do with this problem, okay? You can type this into a calculator and then do mod 10, and that just gives you the last digit, right? So it's not hard to do this. But look, you can also do these by pairs. Let's give you 49, 49, 49. And then when you're working in modular arithmetic, you can reduce at any point. You can reduce all of these. And then what you would be getting, the remainder with 10 here is just the last digit. So you'd be getting 9 times 9 times 9. So this would be 81. You have 9 times 81. You can reduce this mod 10. What is 81 mod 10?
1.
That's right. So this is the same thing as 9 times 1, just congruent to 9 mod 10. So if you want to, you can do these, and I suggest you play around with this because it's kind of a miraculous fact that it can be done. Exploiting shortcuts like this is how we're able to do things like this in cryptography. So we might need to know this number, 24 or whatever. So even though you can never compute this on a calculator, we can still figure out the answer to this question because you can reduce at any point during this process. We'll spend a lot of time on that later. And next problem. So now you have to solve some equations. And we only have 1 minute left, but so all of these are randomized. Remember, you can always just brute force these. So if you want to brute force it, it's fine. Like mod 11, there's only 11 possibilities, so you could try them all. You can also experiment with solving these equations, like 6 plus 11 is congruent to 2. Sorry, 6 plus x is congruent to 2 mod 11. You can try this. So x is congruent to 2 mod minus 6 mod 11. And then, so this would be minus 4 mod 11. You add 11, it's like adding 0. So I can add 11 to this and I get, what is it, 7? Don't trust my arithmetic, but I think, right, if you add 11 to -4, you get 7.
Yes.
Yeah, so the answer here is x equals 7. This is just solving equations in modular arithmetic. For B here, it's like solving the affine cipher. The problem here is if you try to solve 5x plus 1 is congruent to 5, you can do 5x is congruent to 4, that's true. Now you have to divide by 5, so you have to use the inverse. You have to figure out what the inverse of 5 is and multiply it times both sides. So here I'm using 1 over 5 to stand for the inverse, not 0.2. Okay, so it's the inverse of 5, whatever that is, times 4 mod 8, I guess. And for the last one, this problem is called the discrete log problem, and it's actually, there is no efficient way to do this. And the fact that there's no efficient way to do it is exploited in a lot of public key cryptographic algorithms that we'll talk about later. So for this one, there's not anything much better than just trying. So just try some possibilities for C. You're gonna have to brute force it. And that's all the homework. Anybody have any questions on that? Okay. So good to see everybody. I'm gonna take another screenshot. And when I put the, what I'm gonna do is I'm gonna put this video up privately, but let all of you guys see it. And if you still have privacy concerns, then write to me and I will take out the part where I show your email address if you're still not comfortable with that. But I won't make this one public. All right, and I'll see everybody later. I'm experimenting with the 1:30 office hour today. My calculus students will also possibly be there. If you wanted to come at like, I don't know, 1:35, it's kind of hard to predict what the turnout is going to be, but I'll be around waiting for somebody to show up from like 1:30 to 1:40. And if nobody's there by 1:40, I'll probably go. All right, there's one more thing that's been chatted. Let's see what that is. It says, I hate you, professor. You're welcome, so hug. Thank you. And so I've taken the attendance just with a snapshot. And everybody, see you on Thursday.
Great, professor.